In this astronomy example problem, we're going to determine the synodic period of the moon. For example, the time from new moon to new moon, or from first quarter moon to the next first quarter moon, or from full moon to full moon. We're going to start with knowledge of the sidereal period of the moon, 27.3217 days, and there's a nasa.gov website that I use to obtain that number. Two simplifying assumptions here. We're going to assume that the Earth has a circular path around the Sun, and we're going to assume from our point of view the Moon makes a circular path around the Earth. So these are not perfect assumptions, but they'll give us a ballpark answer for this synodic period. Again, the sidereal period is the time between alignment with the same star. Sidereal to the stars, so a time between alignments back towards the same star. And the synodic period is the time back into the same configuration with respect to the sun. So same phase of the moon would be a way of phrasing that. So let's take a look here. I've got some drawings of the situation. There are going to be a number of these drawings. But here's the sun and Earth, new moon, and I draw a line here to some very distant star. This is completely out of scale for a couple of reasons. One of these is the distance from the Earth to the sun divided by the distance from the Earth to the moon. I put in the numbers here, and hopefully I did this calculation correctly, but it's 391. The sun is 391 times farther away from the Earth than is the moon. So the drawing over here, to let you see the moon's orbit at all, this is way out of scale. Here's the sun. So I've got about a factor of 3. There'd be about 3 radii of the moon's orbit to get us to the sun. And the real number should be 391. So just take that into account, please, as we examine this. So the sidereal period, if the Earth was not moving, then we would have from new moon to new moon, and the sidereal period would equal the synodic period, 27.3217 days. That's if the Earth was not moving around the sun. If it was if the Earth and the sun were fixed in space, Earth not moving, the moon's sidereal period would also be its synodic period. It gets back to the same configuration. So why would the synodic period be different? Well, it is because the Earth is moving. As the moon seeks to go around here and get lined up between the Earth and the sun, the Earth is going to travel down on its orbit. So 3 methods of determining the synodic period. This first method is approximate, and it's just to make sketches, and by trial and error, find a number for the synodic period. So I've got the second sketch. We're going to advance the time 27 days, 0.3217. If you remember, this is the sidereal period of the moon. So we're going to let the moon go once around with respect to the stars. Once around with respect to the stars, the sidereal period. How much has the Earth moved around its orbit? Well, that'll be what I'll call theta sketch 2 for the Earth. The angle that the Earth has moved in its orbit. And again, we're assuming circular orbit. I know it's an ellipse, but just for ease of calculation, I've never done the elliptic. Well, maybe I did a long time ago. But the elliptical calculation is much more difficult. So here's our circular calculation for the orbit. And the angle that the Earth would move would be the fraction of a year multiplied by 360 degrees. So here's the amount we're advancing the time, the moon's sidereal period. Here is pretty close to the Earth's, it's not exact, but it's pretty close. This is how many days it takes the Earth to move around the sun, 365.25. And again, our leap year basically results from this quarter day non-integer. So that turns out to be 26.93 degrees. What's the angle for the moon? The moon has gone around one time, and I'm using this star as our reference for angle. The moon is now looking, or the moon from the Earth is lined up with this same star, the sidereal period. these lines may look like they point to different objects, but this star is very, 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 very far away, and these lines are essentially parallel. It's ignorable on how much not parallel they are. So you have to kind of buy into that. This star is very, very far away. The line here to the star, the line here to the star, these are both parallel. So take that as fact. Ask your instructor if you don't believe that. What phase are we for the moon? Well, it's not new moon. The moon would have to be in this position to be new moon. It's in waning crescent. The illumination is getting smaller, so it's waning phase, and it's crescent. Third quarter will be back over here. So it's waning crescent. It hasn't moved far enough, so we need to advance the time a little bit longer. So I've got another diagram for that. Let's go ahead and feed that one in here. So this will be case 3. So I'm just going to go one more day. You know, the moon is at waning crescent. It doesn't have to move a long distance. Let's try just one more day. So one more day, what's the angle for the Earth? Well, now we're at 28.3217. I've just advanced one day beyond the moon's sidereal period. So 28.327. We get an Earth angle in its orbit. It's now gone 27.91 degrees from the start. And the moon, its angle is now, it's one day past the sidereal alignment with the star. So it's moved one day out of its 27.3217 day period. That gives it an angle of 13.18 degrees. Is this new moon? Is it new moon? No, it's still waning crescent. If I have parallel lines here, and the angle up here would be the theta 3, 27.91 degrees. This line, there's 27.91 to this Earth-Sun line, but the moon is short of that. The moon's only at 13.18 degrees. This angle is 27.91 degrees, the same as the angle up here. Again, parallel lines, got a straight line cutting through. So the moon would have to be up at 27.91 degrees to be new moon. It's not. It's only about half that, 13.18 degrees. So that means we need more trial and error. We need to advance another day here. So let's do that calculation. Advancing another day. Now we're 2 days past the sidereal period of the moon, 29.3217. The Earth angle is 28.90 degrees. And for the moon, it's now 2 days past its sidereal period. So that's turns out to be 26.35. We're not there yet. What we're searching for is to get this angle for the moon upward from the direction of the star to be equal to the angle of the Earth downward from the direction to the star. That would give us the configuration where we would again have a new moon. So we're not quite there. How much do you think we should advance? Should we go another day? Well, no, we've pretty much closed the gap. We were at Earth of 27.91, moon of 13 degrees. Now 28.9 for the Earth and 26.35 for the moon. The moon's catching up. The reason for that is that the Earth, in terms of going around a circle, takes more time to complete its circle. The moon takes less time to complete its circle, only 27 days. So the moon is catching up. Let's go just by 0.2 days. Let's just go by 0.2 days and see where we end up. So now we're 0.2 days advanced. So here's our sidereal period of the moon. We're now calculating for the Earth 29.5217. That's how far we've advanced in time since our initial, sorry, I'll pull this back just a little bit. We're now 29.5217 for the time the Earth has been moving. That brings us to 29.1 degrees for the Earth's angle. So right in here, 29.1 degrees. What about the moon? We've now gone 2.2 days past its sidereal period. Again, its sidereal period would bring the moon to here. Now we're 2.2 days past the sidereal period, that motion, and that's 28.99 degrees, about 29 degrees, and you see we're pretty close. So this was 29.52. If you look it up, the actual synodic period is 29.531. So there's the graphical solution, the trial and error solution, and you could refine this if you wanted to. I'm not going to do it, but go ahead and add a little bit extra. Instead of 2.2, add 2.231 and calculate those angles. I'm pretty confident they'll come out the same. That's the first method. The second method would be an analytic method. You already have seen that I'm trying to get these angles to be the same. The angle of the moon up from this line to the star, the angle of the Earth down from that star to be the same. Then that puts the moon right here at the new moon position. So what's the analytic solution? Well, the angle of the Earth and how much angle the Earth has completed in its orbit is this elapsed time divided by the time for the Earth to go around its orbit one time times 360 degrees. The angle for the moon calculation, we take this elapsed time. I'm going to use the same t, the elapsed time, but now I have to subtract off the sidereal period of the moon. For the calculation here, for the angle of the moon, we want just this little distance in here beyond the 27.3217. So I have to subtract off the sidereal period. Again, ask your instructor if you have questions on that. So this will be the number of days we've advanced past our alignment with this star, with our reference star. The subtraction takes care of that, takes care of the moon looping around. So divided by 27.3217 times 360, we get the angle of the moon. What we want is the angle for the Earth equal to the angle of the moon. So I'm going to set these two expressions equal to each other. And if we do that, here is our calculation. And these two expressions equal to each other, right away you can cancel the 360 degrees. That's a common factor on both sides. So t over 365.25 is t minus 27.3217 divided by 27.3217. Cross multiply, and we get this expression, this equation. Multiply both sides by 27.3217, so there's a cancellation on the right side. We've got that coefficient on t on the left side. Multiply both sides by 365.25, there's a cancellation on the left, and we get the I'm now distributing through here, so 365.25 times t, 365.25 times minus 27.3217. And continue with that algebra, gather like terms. So I'm subtracting 27.3217 from both sides. I'm adding this number to both sides, and divide, and there you are, 29.531 days. That's the synodic period of the moon, the time from new moon to new moon, assuming circular orbit for the Earth and circular path around the Earth as we view the moon in its orbit. There's one more way. There is an astronomical equation that lets us calculate the synodic period given the sidereal period and the Earth's period. This equation is appropriate for Venus, Mercury, and the moon. For the outer planets, you put a minus sign in here. I'm not going to bother with that. But I've put in the sidereal period for the moon, the period for the Earth, and S is the synodic period we're trying to find. So I've divided here to create this small number. I've divided here to create an even smaller number. I subtract this smaller number from both sides. I get 1 over S. Then use your calculator. S equals 1 divided by this number, and we get 29.53 days. So there you have it. Sidereal period of the moon given, period of the Earth given. We can find the synodic period of the moon in 3 different ways. So if you enjoy that and you want to see some other astronomy and physics videos, go to these 2 websites, astronomy.gpclements.com. They're free. There's nothing to buy at these sites. There's no registration. Just go ahead and look at the list of videos, and if you enjoy these YouTube videos, please subscribe to my channel.